In this lesson, we're going to discuss how you know what type of model to choose when performing regression and trying to find a curve of best fit for your data. So how do we know when to use a linear, quadratic, or an exponential model? Basically, if you're looking at the table of values, you can, of course, use your difference columns or common ratios to decide that. So, for example, in this first table, we can see that the first differences are all -3. So because the first differences are constant, that tells us that this relationship is linear. Now in our next example, if we were to find the first differences, we would see that they are -3, -1, 1, 2, and 4. So it's not linear. Then we could find the second differences. So from -3 to -1 is an increase of 2, then another increase of 2. Now from 1 to 2 is an increase of 1, and 2 to 4 is an increase of 2 again. So in this case, even the second differences are not exactly the same, but they're pretty close. So in this case, if I was choosing between these three options, I probably would still choose the quadratic model. So because the second differences are almost constant, we'll still use a quadratic model for this one. Sometimes what happens is that your points in your scatter plot don't lie perfectly on a line or a parabola or exponential curve. So in some cases, none of them will be a perfect fit, and you're just looking for the one that would be the closest. Okay, in this last example, you can see that our y values increase rather quickly. And so in every case, we are multiplying by 2. So because the common ratio is all the same, we would use an exponential model for this one. Now, sometimes it's difficult to see if you're just looking at a scatter plot. It can be difficult to see which one's closest, and actually even if you're using the first and second differences or ratios, it can be difficult to tell which one would be best. So in this next example, we're going to go through finding each type of regression, linear, quadratic, and exponential, and using the correlation coefficient to see which one would be the best fit. So this example says in 1990, the total debris in orbit around the Earth was approximately 1,800 tons. The table shows the accumulated mass of debris for the following 5 years. Now, when you enter this table into Desmos, which you'll do after you're done watching this video, when you enter this into Desmos, I would recommend entering 0 to represent 1990 and 1 to represent 1991 and so on, just to make your numbers a little bit smaller in your equations. So first of all, you'll open Desmos and you will enter this data then into a table. Now, because these y values are quite large, you'll want to adjust your window settings. Okay, so to do that, you'll click on the wrench tool in the top right corner of your screen, and you'll adjust the window settings as I've shown you right here. Okay, then you're going to go through and you're going to perform all three types of regression. And what I've given you here in brackets are the formulas you will use. You are familiar with the linear one as well as the quadratic one. And then I've given you the new one for exponential regression. So I want you to go through and perform those three different types of regression. Now, so that you have this to refer back to, what you should get is y equals 1090x plus 1650 with a correlation coefficient of 0.998 for your linear regression. Your quadratic curve of best fit, or your parabola of best fit, should be y equals 45x squared plus 865x plus 1800. The quadratic regression returns only the coefficient of determination, so the r squared value, which is 1. But if r squared is 1, then r is also 1, which we can find by taking the square root. And your exponential curve of best fit would be y equals 2170.4 times 1.2801 to the exponent x. Your r squared value there is 0.986. And your r value then would be the square root of that, so 0.99298. Now, I want you to actually go through that exercise in Desmos to make sure that you get those answers, okay? Then in Part D, it says use each model to predict the mass of space debris in 2005. So in 2005, that would be 15 years after 1990. So when we use the equations we just found, we need to make sure we enter an x value of 15 into each equation. So in your linear equation, if x is 15, then the total space debris is 18,000 tons. If we use the quadratic model, replacing x with 15, then we find an answer of 24,900 tons. And for the exponential model, replacing x with 15, we get an answer of 88,145.11 tons. Now, it asks you which model is the most optimistic. Well, in terms of space debris, I guess the most optimistic model would be the one with the least amount of debris. And so that would be the linear model. The one that's the most pessimistic would be the one with the most debris. That would be the exponential model, because of course that one grows the fastest of the three. And which model fits the data best? Now for that one, we're going to have to look at the r values, and the r value that was closest to 1 was the quadratic r value. So it would be the quadratic model, and that's because the r value is 1. And if you had a situation where there wasn't one that was exactly equal to 1, you would choose the one that was the closest to 1, of course. And that concludes this lesson.